You're watching InTechnology, a video cast where you can get smarter about cybersecurity, sustainability, and technology.
I'm Camille Morhart, host of InTechnology podcast. Very excited to have with me today Thomas Dullien. He's a mathematician, cybersecurity, and software optimization expert who's started one company, sold it to Google, stayed at Google for 8 years, where he worked on Rowhammer. He's part of the first team that was able to essentially identify it as a cybersecurity threat. And then after he left Google, where he also worked on Google Project Zero, he started another company, which was then acquired. We're going to talk to him about a whole range of things. Welcome to the podcast, Thomas.
Thank you for having me.
After our wee technical difficulties on the first try here, I should mention that Thomas is also known as Halvar Flake. Who is that?
So the story behind Halvar Flake is that at the beginning of my career, I was working in reverse engineering with a security background, meaning using reverse engineering to find security vulnerabilities in other people's software. And that sort of work, by its nature, involves breaking EULAs. So a lot of the work I was doing at the beginning of my career was, in some sense, legally risky. And it was more prudent to publish these things under a pseudonym. And so I did at the time. The trouble is that if you start your career under a pseudonym and you do all your important early work under a pseudonym, it gets very difficult to ever get rid of that pseudonym because nobody will, recognize your real name. I haven't actually tried to keep my real name secret in more than 10 years, 15 years. By now, it's still hard to shake off the pseudonym.
And then early on when you were studying math, you had somebody ask you for whom, which sort of surprised you. Can you describe that encounter?
Yeah. So this was Robert Morris Sr., the father of Robert Morris Jr., who was responsible for the first Morris worm, the Morris worm, which was one of the big internet worms at the time that took down the then internet, and who's nowadays perhaps more famous for being the early founders of Y Combinator. But Robert Morris Sr. used to be chief scientist at NSA, and it has a bit of a legendary reputation in cybersecurity circles. So when I met him, I was very intimidated and very starstruck, and we had a very good conversation. And at some point, Bob Morris asked me, "So what do you do?" And I explained to him, "Well, I study mathematics." And he asked for whom. As somebody who was fairly, I wouldn't call it naive, but I was young and idealistic, I didn't quite understand what the for whom was all about. But in the end, it is at the core of what led me later on in my career to reconsider working in cybersecurity and then shifting to software efficiency work. Because the for whom kind of encapsulates that all security work is always about human conflict. You're always working for somebody and against somebody. On the defensive side, a lot of the work ends up being non-technical because you need to get your entire organization into shape. So there's a lot of tasks that involve organization and motivation and skilling people up and just redesigning the org, which is great work, but it's also less of a puzzle. On the offensive side, the work is very technically challenging and very technically interesting. But then you have the trouble, like, who do you want to work for? Particularly on the offensive side, that gets to be very tricky. And I found that optimization work gets a better alignment. For security, if you look at a piece of existing software and you find a security flaw in it, it's very rare that somebody is happy about you finding that flaw and pointing it out. Whereas in efficiency, if you find a problem in legacy software that eats a significant number of CPU cycles and you propose a fix for it, then everybody's happy because the software is now running faster and cheaper than before. So it's much less complicated to deal with the results of your work.
I suppose you're using automation when you're developing this software optimization. Have you already incorporated like machine learning algorithms into the software that you built, or were your company sort of too soon for that?
The company was a little bit too soon, but not a lot too soon. Then again, it's also machine learning and AI is a really interesting field that's developing very rapidly. So when we started out, we were mostly concerned with gathering performance data. Like the entire idea of optimyze at the time was we want to be the one place that gathers performance data from a whole bunch of different companies and then does aggregation and data analysis on top of these things to then make recommendations across the board to everybody to run things faster. Because one of the things that we had observed is that very quickly, the most important libraries in a software stack across multiple companies or even within one big company, will in their computational cost eclipse the most expensive service. So it turns out that the shared libraries are where all the CPU cycles are going. And the idea of Optimize at the time was, if we sit on the treasure trove of data where everybody in the world is spending their CPU cycles, you can do really fascinating things with that data in terms of doing, for example, performance bug bounties, annotating a piece of GitHub and telling people, listen, if you can make this loop 10% faster, we've got $10,000 for you because you're going to save all the customers much more. So the plan was essentially build tooling to gather this performance data and make it really comfortable and easy and convenient for companies to gather that data, and then do analysis on the data, including machine learning and so forth, and then profit. And then due to an unfortunate or fortunate set of events, depending on how you look at it, we ended up getting acquired after we had completed the data collection part, but before we had gotten to the machine learning part. So we didn't do much AI there. That said, we did have some fairly successful experiments after the recent LLM wave arrived at having LLMs explain stack traces to developers, in the sense that a lot of performance measurements will give you, at some point, perhaps a stack trace into the Linux kernel. And then not everybody is very deeply into reading the Linux kernel. And it turns out that in order to get a vague idea of what a stack trace does, an LLM, even if it's not exact in what it's stating, is usually pretty useful to the problem of, can you roughly tell me what this is all about? Plays to the strength of the LLM, which is a vast memory and not necessarily precision in the details of what it's replying.
If you were to look forward, how do you think they're going to be used? I suppose in every sense, right? In the offensive, defensive, as well as software optimization space.
I gave a keynote in 2018 in Moscow, of all places, about the use of AI in computer security. And the thesis I had back then that was reasonably unpopular was that AI and ML works great if you're applying it to distributions that stay stable in time. So let's say facial recognition. Human faces do not evolve at a very rapid rate. Or text comprehension. The way we use language doesn't evolve at a very rapid rate. And it usually works less well if you have a distribution that changes often, or a distribution that changes maliciously. In 2018, a lot of the AI use cases in cybersecurity were aimed at detecting bad or detecting evil. And my thesis at the time was that this is actually using it to select it incorrectly, because you're trying to target a fast-moving distribution or a maliciously changing distribution. And then there's other things that are perhaps more useful. And one of the useful things I was jokingly mentioning in the talk was, at the time, generative adversarial networks had just managed to generate credible human faces. And I had proposed that as a defender, I might be better used to create fake LinkedIn profiles so you find phishing campaigns early than detecting somebody that's actively trying to evade you. Because the distribution of human faces and LinkedIn profiles is much more stable than other things. I joke that using AI to generate fake but plausible looking source code, so attackers that try to steal your source code, steal fake source code, may be a better use of AI on the defensive side. And I feel kind of vindicated by the development since, right? Because we've gotten much better at generating fake LinkedIn profiles or fake but realistic looking source code. And nowadays it may even compile. Like LLMs have gotten so good that you may even get source code that you can build. So yeah. So on the defensive side, I think LLMs will have a huge impact on just generating garbage data. And that sounds like a useless thing, but generating garbage data is actually quite useful, because the attacker usually cannot easily tell good data from bad data, because the people that do the actual hacking are not the domain experts. Like if I'm trying to steal the designs for a military plane, the operators on the attacker side that are moving through the network trying to steal the data do not have the technical expertise to tell fake blueprints from real blueprints. So I think the idea of using AI to generate garbage data for attackers to steal, that may be of big value on the defensive side. On the offensive side, it's a good question. LLMs famously can't plan very well yet, but they can give you a good how-to guide for doing the basics. Because there's a lot of bug bounty and web hacking that is still very labor intensive, and that looks like at least the lower tier could be automated quite well using LLMs. On the performance optimization side, I think there's plenty of great opportunities, not only from LLMs, but also from AlphaZero style algorithms, reinforcement learning algorithms for instruction scheduling, for memory allocation. I think the sky is the limit, really. And I think the hypothesis that we had at Optimize is that having a lot of performance data from different companies and then being able to grind that data and produce output that helps everybody save money and energy, I think the underlying hypothesis is still valid. We just didn't manage to execute on it like we wanted.
If I could also get your perspective, there's a lot sort of right now on Q-star and the possibility that artificial general intelligence is, right at the precipice of, I suppose, a major tipping point. How far along do you think humanity is toward AGI?
Well, this is an answer that is not terribly precise. So I watched an exchange on the artist formerly known as Twitter today, where an AI researcher I follow joked that AGI is always 3 to 5 years in the future. And then Jan LeCun from Meta replied, that's only if you're young and optimistic. If you're more seasoned, it's always 10 to 15 years in the future. So I do not expect the emergence of a general AI for arbitrary tasks that exceeds the human level in the next couple of years. That said, I think the confidence intervals around everybody's estimates have gotten very wide after the sudden jump in performance as the LLM scaled up. Like, we've seen two places, image generation and language generation, where we made a big jump, and a jump that very few people anticipated. If you had told me 3 years ago that we would get text to image in the quality that we're getting now, I would have placed that much further into the future. And similarly, the LLMs now are like, you stare at the way they're being trained and then just predicting the next token, but then at some point, knowing a little bit about the world helps you predict the next token, right? And the fact that there can be a semblance of something like a world model or a basic concept of some things about reality that emerges just from predicting text, that is something that I certainly didn't anticipate. So I think what happened is that we had two developments that violated people's normal prediction. And as such, everybody that is careful about predictions now has to put very wide confidence intervals around any prediction, because we were all a little bit wrong and a little bit surprised. So now we have to take into account that there's a much broader range of possibilities than we thought. On the flip side, AI has a tendency of having these these breakthroughs that then make big progress in one field. And humans have a tendency to do a linear extrapolation from that. So, I mean, we all heard in the mid-2010s early 2010s, like 2013, 14 range, that fully self-driving, fully autonomous cars are just around the corner. And the reality is that nobody expects fully autonomous outside of a prescribed geography to be a thing in the next 6, 7, 8 years, right? So there was a jump in progress. Everybody extrapolated that things would continue at that clip. And then it turned out they didn't. And there was a fundamental thing that we're missing to really make it work. It's very possible that transformer-based LLMs have more or less plateaued in their capability. If I understand correctly, Google's Gemini Ultra is 4 times the size of GPT-4 in terms of parameters, but only beats GPT by like 2 percentage points on most variations. So, I'm not an AI expert at all. I'm not even deeply involved in any of this at the moment, but there's a case to be made that if I need to quadruple the size of my LLM to get 2% better performance, that we may be hitting a similar plateau, at least of this architecture. And until we've got the next breakthrough, things might not proceed at the same clip. But yeah, the other thing I found surprising is that progress in AI was in areas I didn't anticipate, right? It wasn't image generation and text generation where I anticipated progress to happen.
So we're seeing an aggregation of data within hyperscalers. And I wonder if you could talk to us about your feelings as to what this means then for humanity and the accessibility of the data required to build AI moving forward.
So I think the fact that things are centralizing is that's a trend that's been going on for 15 to 20 years in some sense. We had centralized computers in a handful of places in the 50s and 60s. And if you wanted to work in computing, you had no choice but to work in these large institutions that could afford a computer. And then we had the strange anomaly of the PC revolution, which decentralized computing in the 70s and 80s and 90s. And then with the emergence of the internet, you had a trend towards re-centralization, right? Where we've seen the emergence of the internet giants, we've seen the emergence of cloud computing as a consequence of that. So I'm not sure whether, well, AI certainly exacerbates the problem. It's not the first time in the history of humanity where building something was very capital intensive. Like there's no amateur offshore oil drilling, right? It's not something you build in your garage like an offshore drilling rig. And perhaps we're just all very used to this democratizing period where everybody could just build something in their garage. Clearly, I'm hoping that we'll get to a point where computing gets cheap enough, or we get clever, much more clever in using compute to train these models, or we build better models so that we can have less centralization again. It's really hard to make predictions. We don't even know whether, like, will LLM training always be this expensive? Will we make some breakthroughs that accelerate it by a factor of 10x? I think people will put reasonable betting odds on 10x. 100x, perhaps. 1000x, unlikely. I don't know. It's in the end, we know that a human brain runs on a bowl of porridge, right? So we know that you can, like, energetically at least, train things in a much more energy efficient manner.
What is the biggest technical breakthrough you think is required for humanity to make kind of a revolutionary change now, moving forward in technology? Is it a hardware change, a software change? What sort of breakthrough do we need right now?
On the purely theoretical level, getting sample efficient learning. Like you can argue that all the ML models with all their awesome power, they're not very efficient in making use of their data points. I read an article somewhere that we got to superhuman Atari game performance by having an AI play more Atari games than every human has ever played in the history of Atari games. And we got to play Go better than humanity by playing many more games than humanity has ever played in the history of Go. So I think the biggest game changer would be finding a way to be drastically more sample efficient in your use of training data. Because then all sorts of doors open, like being more sample efficient is likely going to be more computationally efficient, and it's going to be much easier to obtain the training data that you need. There's an argument to be made that we're already data constrained in many ways training now. I think there's a big argument where it's alleged that OpenAI used a lot of pirated ebooks to train the model. And now I've also heard that if you exclude those pirated ebooks from your training, your LLM is much worse. So there's an argument that you're already data constrained if you stick to the law. Either we get to be much more efficient with a sample efficiency of our models, or we have to find a way to get more data more quickly, and with that more data, much more compute.
One of the ways that we're getting around large sample sizes, or the problem of needing a lot of data, is actually to create it with the synthetic data. And you're talking about a radically different approach, but I am curious your take on synthetic data.
I mean, people have experimented with having an LLM generate text and then training on the generated text again. But it turns out that this, over time, seems to lead to some sort of collapse in the performance of the model. So training a model on its own data doesn't seem to work quite as well. I'm sure somebody must have tried training one LLM on the data of an ensemble of other LLMs. And I'm sure we're going to experiment a lot with synthetic data. The issue is that I suspect you'll have small creeping mistakes that will creep into your synthetic data over time that then become ground truth for the next model. And you need some sort of corrective process for these things.
Thomas, I don't want to let you go without understanding your involvement in Rowhammer. You are famous in the cybersecurity community for your work therein. So please take a moment and just describe what Rowhammer is for people who aren't familiar with it. And then if you could just describe the role that you played and your team played in understanding what sort of cybersecurity vulnerabilities it posed, which then affected the entire industry and actually still does.
Rowhammer, on the technical level, was an effect where DRAM manufacturers were shipping DRAM chips which had a certain reliability problem, where if you were reading the same memory location repeatedly, essentially putting current on the wire to read out that particular memory location in DRAM would lead to a little bit of charge leaking out of neighboring rows in memory. With the effect that if you were hammering the same place in memory hard enough, then on some neighboring rows for some RAM chips, sometimes an individual bit would flip randomly or non-deterministically. And there was a paper that demonstrated the effect by hooking up a custom FPGA to drive the RAM really hard. And then we discussed that paper internally at Google, and people were like, yeah, this will never be a problem in a real system. And then my colleague, Mark Seaborn, had identified a laptop which actually exhibited the problem. And that was very exciting because in software, you managed to get the bit flips. And then people were wondering, is this just one laptop with bad RAM? So we went to a tech stop at Google and got all the laptops they had, and we tried to reproduce it. And then it turned out that on a good fraction of these laptops, the reproduction would work. And Flippy, we christened the laptop Flippy then for flipping bits. And it turned out that that laptop was just very susceptible to the problem. And that gave us a foothold to then start experimenting with, hey, how do we turn this into a security issue? And people were like, well, it's a random bit flip, you can't do much with it. But then we realized that even if you're flipping a random bit in memory, perhaps you can fill all of memory with something that has a decent chance that a random bit flip will provide you with some value. And then we executed on that idea, and Mark drove it all the way to the finish line and did stellar work there. And then when we demonstrated the problem and that it is a real problem, all hell broke loose with the chip manufacturers generally not being very happy about this, and then the cloud providers not being very happy about it. You can imagine that at that scale and with those amounts of money involved, and also with the economic incentives involved, that out of a sudden the technical problem becomes a big organizational and political problem. And that was very interesting to watch. And the underlying problem doesn't really go away. Like if I'm making DRAM chips, the economics force me to ship the most unreliable chip that my customer cannot tell is unreliable. In the sense that, I mean, like if the customer doesn't notice it's unreliable or will never see an unreliability, it's not a problem for the customer, so they're fine with it. I can't throw away every DRAM chip that has a hint of unreliability in it. The problem that DRAM is still susceptible to flipping bits when it's treated poorly isn't going away, and that's still an issue today. And for me, it was very enlightening in the sense that as a software engineer, you live in this very fake deterministic world, and then you realize at some point that the monocausal determinism that you're used to as a software developer is an illusion created for you by generations of electrical engineers that spent their lives trying to make things monocausal and deterministic. In some sense, it matured me as a scientist, because having been a pure mathematician beforehand and then having done computer stuff, and largely, while my minor was in economics, I hadn't really dealt with experimental science yet. And surprisingly, a lot of the backend engineers at Google that were involved in the response were by education not natural scientists either. So stuff like, we need to estimate how bad this RAM is with reasonable confidence intervals was something that was just not in the bread and butter of everybody's background. And it turns out that, funnily enough, the machine learning folks are much more about empirical experimentation than the classical computer science canon. Yeah, and Rowhammer, for me, really sparked an interest in the physics of computing and what's actually happening during the manufacturing process. I had used computers for many years, for 30 years almost, without ever really wondering, so what's involved in making a chip, and how many weeks does it take to make a chip, and what are all the complications? And then once you stare into that, your mind is blown and changed forever, right? Because the amount of science and the amount of engineering and the amount of very intricate process knowledge is just really amazing in some sense. And it's like, for a nerd like me, it's the greatest show on earth to some extent.
Thomas Dullien, thank you very much. Halvar Flake, pseudonym. But now we all know who you are. Thank you so much for sharing with us, your expertise in mathematics and your thoughts about AI and where it's headed and what sort of technical innovation the world needs next, and your consideration about cybersecurity and working in the space and kind of what it means and where we're headed. Really enjoyed the conversation, and I appreciate your time.
Never miss an episode of InTechnology by following us here on YouTube or wherever you get your audio podcasts.
The views and opinions expressed are those of the guests and author and do not necessarily reflect the official policy or position of Intel Corporation.